Everything you learned about gravity in school is wrong. Well, not completely wrong, but incomplete. Like saying the Earth is flat because it looks flat when you're standing on it. You think gravity is a force pulling you down. It is not. You think the sun's gravity pulls Earth into orbit. It doesn't. You think gravity attracts objects to each other. Wrong again. Gravity isn't just a force. It's something far stranger. Tonight, I'm going to change how you see the universe. And it starts with one simple fact. You're not being pulled down right now. You're being pushed up. Let me explain. For over 200 years, we understood gravity through Isaac Newton's eyes. In 1687, Newton published his law of universal gravitation. It said that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Sounds complicated, but here's what it means. Earth and you pull on each other because both have mass. You and the pencil across the room also pull on each other just so weakly you'd never notice. How weak? If you tried to detect the gravitational pull between two people standing a meter apart, you'd need equipment 10 billion kilometers long, the distance from the Sun to Saturn. That's 39 orders of magnitude weaker than the electromagnetic force. That's why you can feel the tiniest magnet, but you can't feel gravitational attraction to the person next to you. Gravity is absurdly weak on small scales. It only dominates when masses get enormous. Planets, stars, galaxies. Newton's equations worked beautifully. They predicted planetary motion with incredible accuracy. They explained tides, the ocean rising and falling because the moon's gravity pulls on the water. They let astronomers discover Neptune in 1846 by calculating where an unknown planet must be to explain irregularities in Uranus's orbit. For 200 years, Newton's laws were considered complete. But there was a problem. Mercury's orbit was wrong. Mercury orbits the sun in an ellipse that slowly rotates over time, called precession. Newton's equations predicted how much Mercury should precess, but observations showed it was precessing 43 arcseconds more per century than predicted. That's 1/18th of a degree per century. Incredibly small, but real. And unexplained. Scientists looked for explanations. Maybe an undiscovered planet called Vulcan was pulling on Mercury. They searched. It didn't exist. The mystery remained until 1915, when Albert Einstein published his general theory of relativity. And everything changed. Einstein's insight was radical. Gravity isn't a force. It's the curvature of space-time itself. Let me break that down. First, understand that space and time aren't separate. They're woven together into a four-dimensional fabric called spacetime. Not a math trick. Physical reality. You can't have space without time or time without space. And here's the key. Space-time isn't rigid. It's flexible. It can bend and curve. What causes it to curve? Mass and energy. Earth curves the space-time around it. The sun curves space-time even more. Even you curve space-time a tiny amount. Everything with mass warps the fabric of the universe. Think of space-time like a stretched rubber sheet. Place a bowling ball on it. It creates a depression. Roll a marble near the bowling ball, and the marble curves toward it, following the slope of the depression. The marble isn't being pulled. It's just following the straightest path available through curved space. This is gravity. When you drop a ball, it's not being pulled by a force. It's following the straightest possible path through the curved space-time Earth creates. That path happens to curve toward Earth's center. Planets don't orbit because the sun pulls them. They're following the curvature of space-time the sun creates. From the planet's perspective, it's moving in a straight line. But because space-time is curved, that straight line looks like an orbit to us. The planet is constantly falling toward the sun, but moving sideways fast enough to keep missing it. Perpetual free fall. This is why astronauts in orbit feel weightless. They're not beyond Earth's gravity. The gravitational field at the International Space Station is still 90% as strong as on the ground. They feel weightless because they're in free fall, following a geodesic through curved spacetime. You experience the same thing when you jump. For that brief moment in the air, you're in free fall. You're weightless. You don't feel your weight pressing on your feet. Here's where it gets mind-bending. Standing on the ground, you're constantly accelerating upward. The ground is pushing you up at 9.8 meters per second squared, preventing you from following your natural path through curved spacetime. Weight isn't gravity pulling you down. Weight is the ground pushing you up. You're not being pulled. You're being held up against the natural curve of the universe. Right now, you're sitting or standing, feeling the weight of your body. That sensation isn't gravity pulling you down. It's the ground pushing you up, preventing you from following the natural curve of spacetime. If the ground disappeared, you'd fall, not because something suddenly started pulling you, but because you'd finally be free to follow the path spacetime curves for you. This is Einstein's gift, a universe where gravity isn't mysterious action at a distance, but geometry, the shape of reality itself. Mass tells spacetime how to curve. Spacetime tells objects how to move. It's circular, interdependent, elegant. And every GPS satellite, every gravitational wave detection, every planetary orbit confirms it. You live in curved spacetime. Every moment of your life is shaped by its geometry. The next time you feel your weight, remember, you're not being pulled down. You're being held up. The next time something falls, remember it's not being attracted to Earth. It's following the straightest path through warped space. Gravity isn't a force. It's the shape of the universe.